Hello, everybody, and welcome back to Creation Myths. I have what I think is a really interesting one for you today. It's kind of leads me to want to have a longer conversation, almost a meta conversation, on the utility of conversations like the one I'm going to show you. But for today, I'm just going to show you the conversation and talk very briefly about what's going on here. So basically, I hopped on to another, can't help myself, show on the Standing for Truth channel to talk about what I think is the single best piece of evidence for universal common ancestry. I'm not going to talk about what that is right here. You'll see in the show that I'm about to show you. But I want to use this as a jumping off point for a broader conversation about like the whole point of having these conversations and being able to have these conversations with creationists and in front of creation audiences and how you do that and what forums you have to go on in order to have to do that. And I also want to use this to point out something about this particular forum on Standing for Truth, where they've been doing this thing where they have Kent Hovind on for a debate. It's never really a debate with Kent because he doesn't listen and he just uses his script. But they have him on for a debate and then following the debate do like an open mic for some amount of time afterwards, and Kent sticks around for that open mic. I won't go so far as to say he participates in it because he basically just uses it as an opportunity to go to his script, as you'll see. So I hopped into one of these, had a chat, and the interesting thing is that my conversation with Kent was completely unproductive. But then once he left, as you'll see, I was able to have what I think was a very interesting and somewhat technical conversation with Standing for Truth and Rawmatt, a couple other people. I'm as surprised as you are that I just said what I just said. So I hope everybody enjoys that. And then at the end, it is a little bit long, but stick around to the end because the last bit has another interesting wrinkle to it where I actually bring up this problem of basically being unable to have any kind of technical conversation with Kent because he doesn't really know anything about any of the stuff that we're talking about. So that was really interesting to hear what like Standing for Truth and Rawmatt thought about that. And in particular for that, I think it's worth noting what they said to defend Kent and what they didn't say to defend Kent. So again, this is a little bit on the long side, but I think it's useful to illustrate a couple of things, and it's useful as a jumping off point for a broader conversation. And I also want to note that there were a bunch of segments in the middle that I cut out because either they were on different topics or they involved other people in the room in the open mic show that were just talking nonsense and spinning off in all different directions that were completely pointless. But rest assured, anything that was relevant to the topic that I start with about this evidence for universal common ancestry, all that stuff is in there. It's other stuff that I cut out. So it does cut a couple places, and that's just to cut out like complete random conversations that have nothing to do what we're talking about. So again, I hope you enjoy. It's a little bit long. It's got a couple different, I think, interesting things going on. Have a watch.
So most people backstage, I don't have to vet because I am familiar with Dr. Dan, Luca, a couple of legends in the creation versus evolution debate community, and Apologetics 101. So let's start with this so far. And real quick to the audience, though, for those that love a good old open mic night, we do have a couple more for you next week. Dr. Dan, I know Paul Price is definitely going to want you there for this one. So,
man, I'm at work until like 10 p.m. that night.
Oh, no. Okay, we'll have to have someone join and pretend to be you. Maybe they're familiar enough with your argument. So this is next week, Paul Price, Genetic Entropy open mic. And then something a little different, a open mic on the deity of Jesus Christ for all you theological geeks out there. So we got a good mix for you. Okay, let's start with Dr. Dan. Dr. Dan, you probably don't need an introduction at this point, but feel free to give a brief one if you'd like to, plug your channel, and then pick a point or a topic that you'd like to go back and forth with Kent on. Go ahead.
Yeah, hey everybody. Dr. Dan, evolutionary biologist. Channel is Creation Myths. I kind of work my way through the scientific creationist claims that come out of places like AIG and ICR and show why they're nonsense. So talking about stuff like genetic entropy or irreducible complexity, that kind of stuff. Thanks for hosting this. Always a pleasure. Hi, Matt. I think it's the first time we've talked in person. How are you?
Yeah.
The thing is the best evidence for evolution, and I think what we mean by evolution, and correct me if I'm wrong, everybody, but I think we mean universal common ancestry, right? That's kind of what we're like. We don't mean like antibiotic resistance or something. We mean like large scale, right? Am I correct in that? That's what we're talking about, right? Big scale stuff.
Yeah.
That is my objection.
Okay.
The word evolution is too slippery. It is. You're talking about cosmic, chemical, stellar, organic, macro. Nobody's seen life come from non-living material. That would be organic evolution. Nobody's seen that.
I've heard that we don't need to do the script. I agree with you. Let's do universal common ancestry. Because I got it. Okay. I got the evidence right here. It's real straightforward. It's so you actually kind of went into this a couple minutes ago talking about like hypothesis testing and making predictions, and that's exactly what we can do. Donnie, can I share my screen? Is that okay, or do you want me to just talk through it?
If you'd like to share your screen, go ahead. What we'll try and do is, and you're good at this, so I have no concerns, is we'll keep it to one point or one topic at a time for now.
Okay.
It's one thing. So if you'd like to share your screen, feel free to do.
Just a PowerPoint slide. I'm not even going to put it in like a show. I'll just show you the editable view. Okay. So this is where we can get down to it, right? The evidence we want is testable predictions that are different between the creation model and the evolution model, or let's say universal common ancestry, because that's what we want to test. And we can use genetics to do this. And Donnie, I know you're a fan of saying that it all comes down to the genetics, right? That's the thing that actually matters at the end of the day. So what we can do is we can look at genetic sequences that are unconstrained, right? Sequences, that just means that they can mutate basically freely and there's no selection for or against. That's all that means. Me and people here will disagree on whether those sequences are functional or not. It doesn't matter because we can directly observe in the human genome and every genome that exists. We can directly observe that there are sequences where you can mutate it every which way and it just doesn't matter what the sequence is. We can document that, and we should all be able to agree on that. And I want to make sure we agree on that unconstrained regions exist before we go any further. Can we all agree on that point before we keep going?
Yeah, I'm not sure I comprehend what you're saying, and so I'm not going to say, yes, I agree. I think that the fact that we have a complex DNA code indicates a designer.
It's not that, no. Sorry, okay, can I try again to explain it? So basically, Kent, all I'm saying is there are parts of the genome, like there are parts of the genome where if it mutates and it changes the sequence, that hurts us, right? Like it breaks a gene, messes with a protein, and stuff doesn't work. There are other parts of the genome where if it mutates, the sequence doesn't actually matter. And you could just you can change the sequence, you can make it a random sequence and it doesn't matter, right? That's the thing that exists.
Well, let me say that in the English language, there are different ways of saying the same thing. Go hop in the truck, go jump in the truck, go climb in the truck. So the fact that the English language has words that can be used, you're still saying the same thing. Are you claiming that because this genome, some parts of it are a little more flexible than others, therefore this is evidence for evolution? Is that your claim?
No, I'm just making sure we're all using the same definitions is all I'm doing right now. That's just the first thing was just do we agree that there are regions? And it sounds like we do, where whatever the reason for it, we should be able to agree that there are regions where the sequence doesn't matter. That's all I'm saying. That's the starting point, because that allows us to make competing predictions for evolution and creation.
I think the gene code is so complex that we haven't even analyzed all of it. Okay, one human's DNA would stretch across the universe twice, across the solar system twice, tied end to end. So to claim that we know what everything does is laughable. Okay, there may be some.
That's not the point.
So no, I'm not going to.
Can I ask Donnie? Do you understand what I'm saying?
I have a question, Dan.
Are the sequences? Can I just see, Luca, Donnie? Am I being clear about what I'm saying? Like, there are regions of the genome that mutate without cost. That's all I'm saying, and I just want to make sure we agree on that, because that's the basis for making competing predictions. But if we can't agree on that basic thing, then
So it sounds like you're referring to, and I know Matt wanted to say something real quick too. You're referring to conserved regions of the genome versus unconserved or unconstrained sequences that may or may not have a function because they seem to be more fit to endure mutations.
And I will concede, I will stipulate for the purposes of this discussion that the human genome, every genome, I don't care, is 100% functional. I will stipulate that for the purposes of this discussion, as long as we agree, which we should, because this is like obviously the case, that there are regions that can mutate without cost, right? That's all I'm saying.
Some mutate. Okay, Kent, go ahead.
This is, I think, Ken Rock and I show tonight, but I would agree that there are quite a few variations that allow in the human genome. I would also stipulate that we'd have to agree that there are limits. There are parts of the genome that allow you to get, 6 feet tall or 7 feet tall, but none that allow you to get 4,000 feet tall. So there are limits, and I don't think you believe there's limits.
I feel like Kent isn't listening, but I'm going to keep going anyway because we're just going to try.
Dr. Dan,
I'm going to try. Well, hang on. Let me just go through. This is only going to take a minute. I want to make sure that like we can agree on premises before I actually make the argument. But I'm just going to go for it because I feel like Kent's not really listening, but that's okay. So, my cursor, my cursor is visible. That's cool. Okay. So what matters here is right here in the middle, right? So if we have, universal common ancestry, right? It doesn't matter if the sequence is subject to purifying selection or not. We expect to find nested hierarchies no matter what we compare, right? Because everything shares a common ancestor. Now, for the constrained sequences, we expect that to be the case across the board because you can use the common design argument. Now, I don't think that's a good argument, but I'm not arguing against that right now, right? We're not going to do that. But you can use the common design argument to hypothesize that regions that have a sequence constraint, they have to be a certain sequence, they're going to be more similar sequence-wise in organisms that are more similar morphologically, right? There's problems with that. We're not going to worry about it. We're going to accept that premise as valid, right? Now, it's unconstrained sequences between the created groups that are interesting because within a created kind, right, your arc things, your mating pair gets off the arc and then they're going to have their kids and disperse and diversify and everything. That group, within that little group, you actually have common ancestry. So you can look at the mutations that occur within that group and you'll find a nested hierarchy because they do actually, in reality, have common ancestry. For the unconstrained regions that are in different created groups, like dogs and cats and whatever else, right? Those unconstrained regions, those mutations should not be correlated with each other because there's no common ancestry. So there's no, in reality, in the creation model, there's no common ancestry between different created groups. I think that's an uncontroversial statement, right? Different created groups don't share common ancestry. Therefore, the mutations that occur in those groups should be uncorrelated with each other because mutations are probabilistic. They're not deterministic. And that means across the different groups, we don't get a nested hierarchy within the unconstrained sequences, right? That's the hypothesis, or that's the prediction that flows from the creation hypothesis. The hypothesis.
Well, Dan, maybe, and I appreciate you elaborating on your points and arguments. Maybe let's stop there for a second, allow Kent to give his thoughts and feedback. Matt, I know, wanted to give his 2 cents as well on this. So if you don't mind, unless you wanted to quickly wrap up your point.
I would have, Donnie, can you put me on a 2-minute timer?
Sure.
Hit me with a 2-minute timer and we'll do this fast. So these predictions are important because they allow us to distinguish between the two models, right? Because in the common ancestry model, we're going to find nested hierarchies top to bottom. In the creation model, we won't. If we focus on those unconstrained sequences, if you look at this group of organisms right here, compared to this one right here, all the mutations that happen within this tree, right, this clade, this lineage, all of the mutations that happen in here, they'll form a nested hierarchy within here, but they'll be all mixed and matched and completely unconstrained with regard to the ones that happen over here. Now, in the evolution model,
The opposite is true. In the evolution model, you're going to have your birds right here falling out more closely related to your reptiles adjacent to them than they will to like the apes and the other mammals. So according to within the unconstrained sequences, that's your prediction, right? Because of the fact that mutations are probabilistic. Well, what do we actually find when we try to determine the association between these unconstrained regions? We find nested hierarchies across created kinds. So for example, you can do this. This is a figure from a paper from 24 years ago. We could do this. You've got rodents making a nice, neat clade. You've got simians making a nice, neat clade. By any young Earth standard, those are different created kinds, and the sequences used to make this are not functionally constrained. So this is
seconds,
a direct refutation of the common design or separate creation hypothesis. If the topic is what's the best evidence for universal common ancestry, this is it. This is a directly confirmed prediction that doesn't require us to see a cow give birth to a dog, right? This allows us to look in the genomes of living things
10 seconds.
And confirm the evolutionary prediction and refute the creationist prediction. Everyone,
okay, Dan.
Questions?
Dan, okay, Dan, thank you. That was about 3.5 minutes if I also count the first 1.5 minutes. So I appreciate it. What we're going to do is give Kent equal time, let's say 3 to 4 minutes to give his thoughts, his points. And then I'm also going to throw it to Matt as well to get his thoughts. And then Dan, we'll throw it right back to you for a rebuttal. Kent, go ahead.
When I was teaching school 15 years, I would once in a while have a student that was daydreaming and making doodling on paper and making lines on paper. And I would come up and say, hey, we're teaching algebra or trig here or something like that. Take their pen away. Dan, somebody should have taken your pen away. You drew a bunch of lines on paper claiming that there's all the relationships. All you have is lines on paper. We don't ever see a bird produce a non-bird, let alone a crow produce a non-crow. I think man has decided to take all the birds and put them into different categories based on different species. The birds don't care. They know what their kind is. But you are making a claim that birds are related to reptiles. If we go back far enough, we cannot go back, and you don't observe any of that. You believe that, and this is your religion. And you should keep your religion out of science class. If you're an evolutionary biologist, you have mixed two words together that don't belong together. Biology is things that we study about life forms. Bio meaning life. Ology, the study of. The study of all life forms is that cows make cows, dogs make dogs, birds make birds. Evolution has nothing to do with that. There's no such thing as an evolutionary biologist. You need to get a new title. And take your pen away, quit drawing lines on paper. All we see is cows make cows, dogs make dogs, no exceptions. You can imagine all these hierarchies. None of the animals or plants care how we classify them. They don't care. The dogs, when they go out looking for a wife or a husband, they look for another dog. They don't look for a pine tree or a snail. They look for a dog. They know what their kind is. I don't understand how you guys can imagine that if I drew a line on paper connecting them, therefore it's science. That is artwork. That's not science. Go ahead.
Dan, if there's something you want to respond to there, note it down. We will give you a chance. But first, we're going to hand it to Matt. Matt, I know you've been doing some work on this exact topic. And so feel free to convey your thoughts.
Okay. I think I'm off mute. One of the things I just wanted to make sure from Dan was, sequence doesn't matter. You said, but I didn't. I wanted to make sure it doesn't matter for function, or it doesn't matter for building a nested hierarchical pattern.
It's that going back to kind of the very beginning when I started talking, I think is what you're referring to. And
yes.
It's just that there are parts of the genome where the sequence, you can literally have any sequence and there's no fitness, benefit, or cost, no matter what the sequence is. So it can freely mutate without purifying selection that's going to remove the mutations.
Okay.
They're not the whole genome, but there are regions where that's the case.
Right. So when we're talking about the constrained sequences right now, or the conserved one, which undergoes strong selection, these are the strongest constrained regions and that are basically forming this nested hierarchical pattern. So I believe that it was evolution that predicted that these nested hierarchical patterns based on genetics will follow a homology pattern. But now we know that really doesn't work so much. And the reason we say that doesn't work is because these sequences are more based on function. So like, how a hand grows as opposed to how it looks at the end. So Ours is more functional based, not really homology based. So that's what the sequences we're saying are in the created version, or the created kinds version. When you look at baraminology, they're not really looking at genetics. They're just looking at morphology. We don't really look at the morphology because that was a prediction kind of by evolution about what the sequences do. So in our model, we're saying that the sequences are formed, they might form a hierarchical pattern, but no matter where you look in the genome, even these most conserved regions, they'll form different trees. Like looking at cytochrome C, it's a great region, but you go back about 4 steps from humans, or 3 steps, you go from the gorilla to the orangutan, you actually go to a pig, and the pig is 98% genetically similar in that region. And then the orangutan is 97%. Then you go to cytochrome B, and it forms a different tree altogether. So we say that evolution isn't true, even looking at these nested hierarchical patterns and looking at these conserved regions, because we would see evolution in all of them. And the reason we don't look at these highly conserved regions and we look at the mitochondria and the Y chromosome is because they don't repair themselves. They don't undergo recombination like those areas do, and they don't have the strong selection. So that I'll stop. That's too long for me. Sorry.
Yeah, no, I think I got you. So just to be clear though, the hypothesis that I'm talking about and the predictions that flow from the competing hypotheses that I'm talking about are not talking about those regions. That's a separate thing. I just want to be clear about that for everybody. So the constrained versus unconstrained are 2 separate regions. What I'm talking about are going to be like introns and ERVs and retrotransposons, stuff that, functional or not, I don't care. It can mutate and it doesn't have a cost. But
actually, Dan, if I could ask you a clarifying point, are you saying that the unit itself, let's take an endogenous retrovirus, are you saying that not only the endogenous retroviral sequence forms a hierarchy across the biological world, but also the mutations found in the unit itself?
So yes, and we'll get to, I can elaborate on that in a minute, but I just want to finish with Matt's thing, is that so in the unconstrained, so it's for unconstrained and constrained regions, you get these nested hierarchies when you compare sequences. We don't always get the same hierarchy, right? There's parts of the genome where you get an unexpected level of similarity. And there are a couple of different reasons for that we are aware of. So you can have something called incomplete lineage sorting. You can also have horizontal gene transfer. You can also have some, just for whatever reason, the case is that organisms that are not most closely related end up physiologically the most similar. And we don't always understand why that's the case. There are a few regions, right, where like humans and pigs are the most similar instead of humans and chimps or gorilla, right? It's not even an ape that's the most similar. And that's fine because
we find that with the Y chromosome too, right? The chimp and gorilla Y.
No, that's structural rather than sequence. It's
well, with the Y chromosome, if you were to consider overall gene content, architecture, and size differences, the chimpanzee Y and the gorilla Y are more similar to each other than either are to the chimpanzee Y. When you consider everything, not just content or size differences, Dan, but everything.
I don't want it. So 2 things. 1, I don't want to get off topic. But 2, you can't aggregate factors like that. It's lumping apples and oranges and bananas together in the same bucket and then comparing the amount of fruit instead of one at a time. But I don't want to get off topic. What I just want to finish with Matt's point is that yes, there are these regions where we do find unexpected relationships. But what we find is that when we generate the nested hierarchies, genome wide, and we use the largest possible regions of the genome, you end up on average finding, for example, humans and chimps, then humans and chimps and gorillas, and the primates within the mammals, and all the mammals together rather than the mammals mixing and matching with the birds, right? It's you look at these things on average.
Yeah, but I think Matt is pointing out that you do find quite a bit of lack of uniqueness in those nested hierarchical patterns when you actually start to dig a little deeper and you look at certain sequences. If you look at, orphan genes, I know you've discussed that. There's no real consistent hierarchy there. I just want to say this, and for the guys, listen, let's take one point at a time. I do, for the audience sake, I do want to provide this visual, Dan, because I don't
like I said,
think
I'm
what
not
you're
interested.
saying.
I came to talk about one specific thing.
But
about the
Dan, I
hypothesis
don't want you to
testing,
slap
so
and run. I don't want you to slap and
change
run
the
because you
topic.
said listen, Dan, you implied that I was wrong about the Y chromosomal
Mm-hmm.
dissimilarity, but here is a visual from a 2020 paper, or 2017 to be specific. You have the human Y chromosome right here. You have the chimpanzee Y chromosome right off the bat. It's half the size. You can see the gorilla Y chromosome here. That's why I'm saying if you compare overall gene content, architecture, and size differences, you have the human Y more similar to the gorilla Y than either are to the chimpanzee Y. And that's my point about your argument, is it's the differences that make all the differences. So yes, we do find a general hierarchical pattern in the biological world if you look at anatomy, morphology, physiology, and genetics, like you're saying, but it's the incredible dissimilarities that we find an inconsistency in the hierarchy that I think the evolutionary model has a problem with, and some very serious problems.
I want to ask, hey Donnie, I got a follow-up question with it, specifically with this figure right here. So first thing, I want to just have everyone just read the reference on the right there. So it's the sex chromosomes of great apes compared cytogenetically, ideograms of G banded. Okay, so this is a banding pattern that has to do with like the density of the DNA and the packaging of the DNA and the affinity of the DNA for things like proteins. It's not sequence specific. So my question is this, Donnie, there's that big like kind of grayed out band at the bottom of the human Y chromosome here. Can you just read what the I can't see it because it's too small. What is that on the left right next to that gray big fat part? Yeah, right there. What does that say? Words that
that's
are
heterochromatin.
Okay, so that's heterochromatin. That's going to be largely
densely packed pieces of DNA. I understand we talked about that before. Largely comprises, repetitive elements like satellite DNA. But the point is, but notice.
I have a question.
I do want to make sure Kent gets in on this.
Okay, he can go, but I got a clarifying question here. If you that heterochromatin is largely repetitive stuff that's densely packaged all the time. If you compare the sequences.
Just one second. We'll let Dan finish his thoughts. We're going to throw it right back to you, Kent, and then we'll have to bring someone else into it too.
If you compare,
Donnie, shut his mic off, please. This guy is hogging the whole problem, the whole program. Get his own show. He is giving what is classically known as the snow job. Okay, this is baloney. He's drawing lines on paper, drawing conclusions from stuff that's crazy. Please get another guest in here. Okay, get somebody else in here. I'll debate him on a different day by himself. He wants to hog this whole program. I got lots to do. Okay,
look, Donnie, you asked me a question. I'm happy.
Donnie.
Okay, guys, I'm going to jump in because order in the court. So we're going to bring in somebody. We're going to bring.
Hang on, go back to the Y chromosome. Let's wrap that up, and then I'll peace out.
Donnie, you're the moderator. He's doing it again. Get a new guest. Get a new question, please, from somebody else. Okay, he can go get his own program. He's drawing lines on paper. He's giving us artwork. I'm not interested. I want science. Go ahead.
Dan, to be fair, we have gone for about 22 minutes with just you. Your points are technical, and so they require more time for you to explain. But we are 22 minutes.
Jump in again. He doesn't get the message. He's not getting it. Okay, shut him off. Get somebody else. Go ahead.
Okay. To be fair, we're going to move to the next
sequence. Which one's more similar, human, chip, or gorilla?
Donnie, do you understand? I would throw that student out of class. Okay, go ahead.
Okay, guys, we're going to be here for a couple hours after too, but you'll probably be sleeping. No worries. Okay, we're going to move on to Luca now. Brian, next on the panel. Appreciate your patience. How you been? And
great.
You had a question. Go ahead.
Well, originally I wanted to ask the other guy the question because he said that for some reason he said that he did that because Ken asked him if he believed that if you go back far enough, you think what was it? They were related to elephants or something like that. And he said that he didn't believe that, which is kind of odd. So I was going to ask him why he said that, because usually most evolutionists would answer yes if it's an ultimate question of relationship. But any given case, since everybody's on the similarity track, I would like to ask the evolutionists in the room, and Kent as well on that. If I know a lot of these guys don't believe in God, but from our perspective, do they not think that God could create different organisms with different variations of similarity and dissimilarity. Now that's from our perspective, but that's how we're looking at it. And so I was wondering if they would concede to that point that it is possible that God could have created with those types of variations with similarity and dissimilarity.
If it's my turn, God, I believe, created all the plants and animals with an amazing ability to produce a variety of offspring that can survive in different climates. There are dogs that can survive in the cold weather. There are dogs that cannot survive in the cold weather. There's dogs that can only survive in hot climates. We have dogs with long fur, long hair, some with short hair, some with skinny legs, some with fat legs. I think they're still dogs, and they had a common ancestor called a dog. So I think it would be wise for God to create all the animals with a gene code that contains variations within limits. It's always going to be a dog, but you might get a dog that's able to survive, Alaskan winters. And other animals simply could not survive that. If you turned all the Chihuahuas loose in Alaska out in the woods, none of them would be there in the spring. Okay, they'd all be dead. So they can't survive. So I think the fact that the animals have a gene code, and so do humans, by the way, for skin color and height and eye color and hair color, there's a variety. They're still human. The variations happen and they're limited to the same kind, which is exactly what I've always been saying. Show me an example where any animal or plant produced something that's a different kind. There are 8 varieties of squirrels. Probably had a common ancestor called a squirrel. That's to say a squirrel and a banana are related, though, is not science. It's a religious belief. That's why these charts they put in the textbook, humans and birds and reptiles and ladybugs having a common ancestor. This is propaganda. This is artwork. This isn't science. So, yes, Brian, I believe that variations can happen, certainly, and they're limited.
Brian, appreciate it. And you said you wanted one of the evolutionists to give their thoughts on that too, Brian, or was that just for Ken?
Just across the room if you want to.
Okay. Evolutionist leaning folks here would be Jackson Rowe. Good to have you, Jackson. I think you and Kent know each other.
Hey, what's going on,
Only
guys?
debated about 50 times. And then Dr. Dan. So whoever wanted to answer that, feel free to go ahead.
I'd be happy to, but Jackson hasn't had time yet, so I'm happy to give him time.
Oh, it's all right. I'm feeling kind of bad because I just got back from my grandmother's and I ate way too much and I need to chill for a second. So I'll let Dr. Dan have that one.
Let that food digest a bit before engaging in the debate dojo, right, Jackson? Okay, Dan, go ahead.
Yeah. So right. So this is kind of what I was talking about before, that like under a common design or a creation model, you can say like we expect similarities based on function, based on morphology, whatever you want, just because the creator, the designer, whoever, right, made things that way at the beginning of the process, right? That's totally, yes, that is a legitimate hypothesis, and we can test that hypothesis. The way we test that is by looking at sequences that mutate without purifying selection, because those sequences shouldn't maintain that nested pattern over time because mutations are going to happen. Whereas sequences that are functional, that are limited, that are constrained, those are going to, maintain that pattern. So like you talk about a specific gene, right? Like opsins in the eyes is a good example where all eyes have opsins, and you make a nested hierarchy with eye opsins, and it basically follows the morphology for like worms and vertebrates and arthropods and mollusks, right? It basically follows the pattern you'd expect. But if you do the same thing for those same groups of organisms for regions that are not constrained, like introns in those same opsin genes, the introns specifically, then you don't get that. Then you under the creation model, you shouldn't get that pattern, because those regions are just, they started separate. Even if they started identical, the way they would change since creation is going to be unrelated to each other, right? Because they are in actuality separate lineages without common ancestry. So they're going to be uncorrelated with each other. But in reality, we still find the same nested hierarchy. So yes, that is a legitimate hypothesis. We can test that, and the predictions that flow from it are not met.
Okay, Dan, thank you very much. Brian, if you had something follow up or to follow up with, or Kent, if you wanted to respond. Matt, I saw you unmute. So whoever
Yeah,
would like to go next, go ahead.
I'm not convinced that I answered because in the creation model, okay, we would see that that God can create with a wide variety. Okay, to start with, of course, we got tons and tons of information to work off of, and we do believe in variations within a kind, and we also believe that God created all organisms with all sorts of similarities and differences, and so between kinds, for example, you can find similarities, but you can also find differences. And we don't know why that God created, with all those different differences and similarities, but we know that exist. But within our paradigm, we do accept the fact that all organisms have similarities and dissimilarities. What we would probably reject is that such similarities automatically prove common descent of all life forms, and plants and animals and things like that. And that's ultimately what we would reject. And I just don't see that somehow pointing to similarity would automatically vindicate the evolutionary perspective. To me, it seems like a kind of a error called confirmation bias, where you don't consider what the other side is actually saying, because technically speaking, the other side, the creationist side, also predicts similarity and dissimilarity. So and of course we also accept variations within a kind. So we can accept, for example, all the different kinds of breeds of dogs, and we can accept that wolves and dogs are related and that sort of thing. But we would not say that.
Okay, Brian, I appreciate it. I do want to make sure Kent gets involved again.
Oh, yeah. I just wanted to get my perspective there. I'm sorry, I didn't mean to go that long.
Can I ask a clarifying question?
Donnie,
and I don't want to respond to the
I've
answer.
only got a few minutes left here, Donnie. So would you?
Yeah.
Dan obviously wants to monopolize the whole conversation. I told him to get his own show. I think he's got that. Go ahead, use it on your show. He keeps talking about these constrained sequences and stuff like that. This is all arbitrary stuff that man is doing to these animals and plants and creatures, looking at their DNA, trying to put them in this category and that category. They don't care. They know what their kind is. Cows make baby cows every time. To imagine that this is proof that cows are related to birds is stupid. It's not science. Don't teach it as science. We observe and we see that some people say 250, some say 450 breeds of cows. I don't care. The cows don't care. They look for another cow to mate with. They bring forth after their kind. This is all that's been observed. He wants to put them in different sequences and look at the gene code, and this one is similar to that one. The cows don't care. They might have a similar gene code to a pine tree. They're not going to try to mate with the pine tree. So the Bible so far has made this claim that they're going to bring forth after their kind. This has never been refuted. I can't prove that it's always going to be that way, but so far that's all we've observed. Science, what we can observe, study, test. I think the Bible made a real scientific statement when it said they will bring forth after their kind. That's all we've seen. And then they're going to argue, what's a kind? Well, here, species, definition of species, a kind. Oh, look at that. Synonyms for species, a kind. The whole argument about species and kind, that's what they're going to go to next. They always do, okay? They don't have a good definition of species. If they can bring forth, they're the same kind. Cows and pine trees cannot bring forth a baby. Cows and apples cannot bring forth a baby. They're a different kind. Is the cow and the buffalo the same kind? That's a good one. I think they made beefalo, so maybe they are the same kind. But their whole argument is they try to muddy the water, which is what he's going to try to do here in a second, and make so we've created these constrained sequences. The animals don't care how we constrain them or sequence them. They know what their kind is. So, and I'm out of gas, brother. I got just a few more minutes and got to go. But go ahead. Who's next?
Okay, let's now. To be fair, I know. Well, we've got T-Rock, Jackson Rowe, Centurion, Theo, but most here are now creationists. So I'm guessing, a quick question. At the 2-hour mark, again, we will still continue the open mic. So again, anyone's feel free to stay. And so why don't we Okay, you know what, Dan, to be fair, since you're one of the two evolutionists here, let's give you 1 minute to respond. Now, since we're really winding down, I'm going to feel free 1 minute to respond, then we'll give it back to Kent for a minute, okay?
That's fair. I don't have anything to say to Kent. Is he just doing his script? But I do have a question for, sorry, I just know Apologetics 101. I don't know your actual name. I apologize. It's nice to chat with you. Brian, so I just have a question because you were saying that God could create similarities and patterns and everything. All good. My clarifying question is it a one-time creation or is it an ongoing intervention as things diversify?
One-time creation, but I do think that God created us with a wide variety of information in there.
Okay, so it's a one-time thing without subsequent intervention after creation, just to be clear. Okay, cool. Thanks. That's it. That's all I wanted to clarify. Thank you.
Okay, thank you, Dan. Thank you, Brian.
But before we go on more on that one, I did want to touch on the one thing you posted on the side. You put young Earth creation predicting no nested hierarchical across created kinds. You in the unconstrained regions. Yeah, we'll go to that one real quick.
Yeah, sure.
If anybody wants to chime in, feel free. I'm not very good at moderating, but I'm going to keep doing it. We have you said that the areas that mutated without selection, such as introns. But if we look at introns, then we're stuck with only eukaryotic organisms, right? Because introns aren't found in other things.
Yes.
So we must not be able, but it still builds a nested hierarchical tree just in eukaryotes.
If you're willing to concede that all eukaryotes share common ancestry based on those data, then I am willing to say, I don't care if prokaryotes do as well.
Okay.
I'm willing to meet you halfway on that.
Mm-hmm. All right, no big deal. I wasn't going to get into that. I just wanted to know what type of trees does this form. I didn't know that you young Earth creationists didn't predict that there would be no nested hierarchical patterns looking at junk DNA or introns or any of the unconserved regions.
Well, so it has to be because God, I'm so bad. I apologize. I started my new semester today and I learned a bajillion names. Was it Brian?
Yeah.
Brian?
Yeah, up there. Yeah, good one.
Good. Still in my short-term memory there. So it's that and Matt, you tell me if you disagree, but I clarified with Brian that it was a one-time creation event, right? So all these different genomes, and they may have hierarchical relationships at creation, right? Based on whatever criteria. And that's cool with me. I'm down with that, right? But then because they're going to mutate from that point, they could start out identical, they could start out in a nested hierarchy, whatever they start at.
Right.
Once you hit that first domino, they're going to mutate in a way that's not going to be correlated with each other because mutations are probabilistic rather than deterministic, right? Well, good. So if you got, say, the primates, right? Let's just say primate kind. I don't want to get into what a kind is. Let's just say, right? Yeah. Primate kind. They're going to have these sequences, ERVs and introns and whatever, and they're going to have whatever mutations they experience. The rodents, relatively closely related, are going to have a different set of mutations occurring because they're actually separate kinds, right? So you should not be able to generate a nested hierarchy showing those two clades separate from each other. They should be mixed in using those uncorrelated sequences for comparison because they're actually different in terms of their ancestry and they don't experience the same mutations in the same order. But what we actually find is even when you compare those uncorrelated sequences, that you still get the nested hierarchies. And that's only a prediction that you get from common ancestry. You predict the opposite from separate ancestry.
Okay, well, I would say that one, we're finding that most regions, even the conserved ones for the most part, have a very quick mutation rate. So if we go over and we say, okay, we find mutation, what's that?
I said that's okay. That's okay because it's not how fast the mutations happen; it's that they're different. That they're
where they're happening, right?
Yeah.
Okay, so we're finding that mutations aren't as random as we thought they were. For example, you take dogs and people and you put them in the same location, they get the same type of cancer. They're not sure if it's from drinking the same water or breathing the same bad polluted air in a city. But we would say that these sequences, when they do mutate, we're going to get the same repercussions. And so wherever those repercussions are happening, even in junk regions or endogenous retroviruses, you're still getting cancers and diseases from them. That would be in the genetic entropy aspect of the things.
That's fine. That's completely different from what I'm talking about. That's a whole separate argument.
Okay. So we're talking about then just a purely nested hierarchical pattern. Just the nested hierarchical pattern.
Say that again.
Oh, sorry. We're only going to be talking about the nested hierarchical patterns of those mutations and the introns and everything then, right?
In the unconstrained regions. That's the key.
Okay.
Yeah.
So if
Matt, and before Matt answers, earlier, Dan, you said you were willing to concede for sake of argument that all of these unconstrained regions were functional.
Yeah, because you can have functional regions where the size matters, but not the sequence. You can have functional regions where it just has to be a bunch of hydrophobic amino acids, but which specific amino acid doesn't really matter that much, right? You can have a bunch of reasons why a region might be functional, but also the actual sequence of nucleotides either doesn't matter at all or is highly flexible, right? And I'm happy for this specific thing I'm talking about with the nested hierarchies in unconstrained regions. I am happy to stipulate for the sake of argument that the entire genome is 100% functional, but we should all be able to agree that some parts of the genome are not under purifying selection, because that's a direct observation that's easy to show.
Okay, so you're saying that the functionality aspect of this argument is overall agnostic, because we'd agree that there's some areas in the genome, evolutionists and creationists, that are more prone to mutation accumulation than others, right?
Yeah.
A conserved region that's important in the heart or brain development, that's not going to be able to endure mutations in the same way that maybe a non-coding region of the genome that's involved in acting as a mutational buffer or something like that.
Yes, absolutely.
Okay, so you're essentially saying those areas of the genome, the non-constrained areas of the genome, they, from the creationist perspective, they're being hit with mutations over the course of the last 4,500 years, and so we shouldn't find any hierarchical patterns if creation is true.
Correct.
Okay.
Across, I want to be clear, across created kinds. So like within the dogs, for example, you would still find a hierarchical pattern because all the dogs in the creation model are related to each other, right? But if you were to compare dogs to cats, you shouldn't get two neat clades because in the creation model, they're unrelated to each other. Does that make sense?
Yes.
Yeah,
So,
let me respond to Dr. Dan's points.
Okay, so T-Rock, will go you, then we'll go Matt, then we'll throw it back to Dan. So I think everybody on the panel is now on the same page in terms of what we're dealing with.
Yeah.
So T-Rock, go ahead. Hand it back to Dan. Matt, go ahead.
Okay. I was just taking notes from a whole bunch of different things. The first one was, so if these patterns are not similar, and as far as nested hierarchical patterns go, even when looking at conserved regions, and you have to take into account horizontal gene transfer and other factors into account just to make it work, then why trust it? If everything should be similarly kind of pointing to a consistent tree of life kind of everywhere you're looking, especially if we're talking about selection being so powerful. And then if mutations are accumulating so fast, then how can deep time be possible? Because it would have erased genetic similarity over massive amounts of time. Let's take cats, for example. We can, the guy earlier, Luca, mentioned that you can take a plant, rip off of something and graft it onto another plant and it'll take. Well, we can do the same thing with a cat. You can take fur off of it and it'll graft from a lion even onto your little house cat. But if deep time had actually occurred, then that would be, completely impossible, right? We have cats that are 3.8 million years old, but yet they can all interbreed with each other with, of course, the restrictions of size, but they can all breed and create hybrids. So my thing would be that, there's some nested hierarchical patterns that do exist, but we account for these based on their function. And since Dan said, okay, I'm fine with function, then we would say, well, that's good, because that's kind of all our model is really based on. And of course, there's going to be some type of a pattern, because we weren't created as empty shells. We were created with different sequences. Like, we'd be dead if we didn't have telomeres. So when we see telomere sequences, that's kind of expected. We're all life, and it's going to have some type of padding to protect your chromosomes, right? So we expect that there's going to be some nested hierarchical patterns if you're looking for these things. I just don't know how to answer his question on the introns. So that's luckily why Donnie is here. His specialty on that one. So I hope we'll get to that one for you. And then another question that had came up was what would be the best evidence for evolution? I think it was Luca asking Kent for that. And he said, what evidence can I bring to the table? Mine would be these experiments with fast evolving organisms, slowly micro evolving morphological features into macro evolutionary changes. That would probably be the best way to start. But there you go.
Okay, thank you, Matt. Let's throw it back to Dan. Dan, feel free to respond to anything you'd like to.
And then from Matt, it basically, you're pointing out something accurate, which is that when you look at genes, you look at, whatever parts of the genome, you do find exceptions to the expected hierarchical pattern. Is that a fair kind of summary of what you're saying?
Yeah, exactly.
Yeah. And that's true. And evolution needs to be able to explain that. The cool thing is we can. Because couple responses to the therefore we should say separate ancestry kind of argument that flows from that. One is that we understand the processes that lead to that, like horizontal gene transfer, and we're really good at detecting that. There's computer programs that are really good at finding recombinant areas. And when you do phylogenetics, you have to remove those areas because we understand it messes up your stuff. And you want to just focus on vertical ancestry. The second thing is that there are processes like that, like incomplete lineage sorting, where we can predict the degree of weirdness that we expect to see. Like, for example, how frequently should we find a sequence where the chimps and the gorillas are more similar to each other than either of them are to the humans? What we expect is human and chimp and then gorilla the third one. Sometimes we find chimp and gorilla and human the third one, or human and gorilla and chimp the third one. The thing is, we can predict how frequently that should happen based on what we think we know about the divergence times, and our predictions in that regard are accurate. And that's called incomplete lineage sorting, and it's an expected thing that happens in evolutionary history. And then the very last thing you said, the second to last thing, but I'll leave the last one because it's a different topic, is fast mutation rates. How is that possible? It's because over long periods of time, it's because most mutations don't stick around, and the long-term substitution rate is a lot slower. And we can directly document that using those pedigrees I talked about that are direct observations, but they only go back, 4-5 generations. And you can see that divergence between the mutation and the substitution rate. So that's why you can have these long, millions of years and still have these close similarities between things, because the substitution rate is slower than the mutation rate. I think I covered everything. Thank you for giving me the time.
On this topic because I've been wanting to get in on this since T-Rock initially had his statement, I wanted to go after T-Rock, was basically what I feel like all the creationists have been missing about Dan's argument is the very first point that he couldn't get y'all to agree about, which is the existence of non-constrained sequences. You have to start with that. I mean, the reason why, all of you, I feel like, have been avoiding that question, because if you accept that, Dr. Dan's argument flows very easily through a chain of logic. So it seems like you're getting hung up on that, but you're not wanting to address whether or not unconstrained sequences exist, like T-Rock bringing up that, oh, well, we would expect that if organisms are all eating the same kind of food on a biochemical level, then we would expect there to be similarities in their genomes. But inherent in that, for him to be able to make that reply, the inherent assumption in that is that these unconstrained regions that Dan is talking about are somehow important for your functionality of being able to metabolize or eat your food that you eat, which we don't have evidence for. These are unconstrained sequences. Even if they do have function, you want to say the genome's 100% functional. Even if it's 100% functional, if there are unconstrained sequences, that means that their function is not tied to their sequence. And as long as you accept that unconstrained sequences do in fact exist, and there's plenty of evidence for that, then his argument follows logically. So you have to address, I want to hear you guys, when you respond, say, yes, I think unconstrained sequences exist, or no, I don't think they exist, and explain why.
No.
Okay. No, guys, I'm moderating. Please, Bubbles. I don't want people just jumping in the second someone stops. Grayson, thank you for your points. But anyways, on the hierarchies argument and the with the unconstrained sequences, the question I would have, and so whatever evolutionist wants to go after me, I'd appreciate if you'd answer it. I'm kind of curious, according to the evolutionary model, if you have millions and millions of years for unconstrained regions within the genome to basically accumulate all of these mutations, why wouldn't they erase these genetic signatures of these nested hierarchical patterns in those regions? Why do they exist at all if deep time evolution was true? And I'll just ask the one question so we can kind of go one topic at a time. So whoever wants to tackle that one next, go ahead.
Sure, I'll take that one. It's because substitution rates are slow. So when you have a big genome with lots of real estate for mutations to occur, and you have a relatively slow rate of accumulation, you're able to generate, you're able to determine patterns of similarity over long distances in time without running into a saturation problem. So like, for example, you can look at regions that mutate, or I should say that accumulate mutations very quickly, right? You can look, for example, at the control region of the mitochondrial genome, and you can compare that across apes or primates or mammals or vertebrates. It gets difficult to use that as a basis across like prokaryotes and, well, obviously not prokaryotes don't have it, but like across, actually, if you look at the proteobacterial genome, they kind of do. Across large distances, it's difficult to use a rapidly mutating region like that. But you can use constrained regions that accumulate substitutions much more slowly across those vast distances. So you can compare prokaryotes and eukaryotes using the ribosomal DNA sequences, because those are very tightly constrained and have a much lower substitution rate. So it's true that some regions of the genome, particularly the unconstrained ones, are going to accumulate differences very fast. Those regions are not going to be useful across like animals versus plants versus rhizarians, right? Because there are two different from each other. You have to use slower evolving regions to make those large scale comparisons.
So you're arguing from the substitution rate within unconstrained sequences. You're saying that the substitution rate is very slow, and so major changes don't accumulate quickly, as compared to your per generation rate in unconstrained sequences that are fast.
Other way around. It's specifically in highly constrained regions where you're going to have strong purifying selection that you're going to see the slowest substitution rate. So like your ribosomal sequences are like consistent across all of eukaryotes, right? So
it's
like
detrimental to the health of an organism, right? Basically.
Right. So like you can't compare like human and chimp ribosomal DNA and get a nice neat pattern, because they've been apart for such a little amount of time, relatively speaking. They're basically identical to each other. You have to pick a faster evolving region to resolve that relationship. But you can compare prokaryotes and eukaryotes and resolve the relationship using those very slow evolving regions. So it's different parts of the genome accumulate substitutions at different rates, and some parts are going to be informative across short time scales. Some parts are going to be informative across long time scales. And you just have to kind of know which parts to compare, because if you compare the fast evolving parts over long times or the slow evolving parts over short times, you're not going to get informative comparisons. It's just going to be a mush.
That sounds like special pleading, though.
Okay, go ahead.
I was going to say, that sounds like special pleading. But even if I grant you this, just because they have high mutation rates doesn't mean these mutations are constructive. I mean, they're random, correct?
That's a separate thing. I like to use the word probabilistic rather than random, because random makes people think that they're all equally likely, which is not the case. Certain types of mutations are more likely than others, and certain regions experience mutations faster than others. So it's not the case that every mutation is equally likely. But mutations are probabilistic rather than deterministic.
BRB.
Now, for sake of argument, if mutations were more so deterministic than probabilistic, what would that mean for your argument, Dr. Dan?
So then if you think back, like however, an hour and 2 hours, whatever it was, if you think back when I showed you that table with the different predictions, then it would all be the same. If mutations were deterministic, then that goes away. Now,
Okay.
there have been a lot of studies on this trying to determine if mutations are probabilistic or deterministic. We've known since the 1940s, the famous fluctuation test, the Luria-Delbruck fluctuation test, that they are probabilistic, not deterministic. There have been a couple of papers recently that there were a lot of headlines saying that, no, that's wrong. And those papers turned out to not be very good. What they showed was something that we know, which is that certain regions of the genome often mutate faster than others, and some organisms can modulate the rate of mutations in a region-specific way. So they can cause a specific region of their genome to mutate faster. But the mutations that happen are still probabilistic. They can't make specific mutations occur. They can just increase the rate in parts of their genome.
Okay. I do have a couple points I want to make. I'm going to save them for a second. Throw it back to Matt. Matt, go ahead. What are your thoughts on that? Anything that's been said, let's say in the last few minutes?
Sure. If you guys like numbers, so this one will be fun. If we go for selection, how strong is it? Well, we have to look into a really conserved region. My favorite is the CO1 gene, which is highly constrained. If we look in humans, we find anywhere between 0 mutations and 10, with lots of them having very few. Now, if we put evolution to the test using their dates, and we look at chimpanzees, our closest relative, we get about 65 mutations on average in them in the CO1 gene, and that's over 200,000 years. Now, you go back 7 million years or 14 million years. We'll just go with the lowest number on this one. So now we have mutations accumulating and going to every single bottleneck. Why this matters is because over 200,000 years to get to 7 million years, you have to multiply that times 35. That's when you get to the split. So if we have 65 mutations on average looking at chimpanzees, and then we multiply that times 35, we should find 2,275 random mutations in a small CO1 gene region of just 650 base pairs. But yet we don't see that at all. We're very genetically similar in that region. So what's going on? Why would selection be removing them if we're seeing diversity increase constantly? Selection would be removing diversity, but yet we see genetic diversity.
And that's what's happening. Right. It's so you started that by saying that this is a highly conserved region of the genome, which means it's highly constrained. It's under purifying selection. So it's an important thing that we need to function correctly. So if you mess with it too much, it's not going to work. So you're going to have strong selection against changing it too much. So if every mutation that occurred persisted, then you would see, 65,000, however many differences it would be. But most of those mutations are going to cause a problem because it's a highly constrained region that's really important for physiology. So natural selection selects out, which is to say the individuals that have those mutations either don't have as many kids or maybe they die, right? So most of those mutations that have occurred historically in that gene since the split between the human-chimp common ancestor, most of those mutations don't still exist in living populations. Only the mutations that were tolerable to the function of that gene still exist. That's why you see that discrepancy between the linear rate, if you just projected the mutation rate backwards, and the substitution rate, the accumulation rate that we actually see. That explains the discrepancy.
I want to make a point. I've been taking notes, and I think I get what your previous argument was on the substitution rate. I feel like it was a little vague and convoluted, but maybe you can clear a few things up, because if it's unconstrained, like we're dealing with here, it's then substituting through drift randomly. And so should scramble or basically just mutate those regions randomly, erasing this hierarchy signature that we find. And so I'm still curious why we find a hierarchy at all in these unconstrained regions if deep time evolution were true, Dan.
Well, so I just want to make sure I didn't misunderstand Matt. Matt, the region you were talking about was highly constrained, right? It's a gene that's important, right?
Yeah, that's a respiratory.
Okay, cool.
Correct.
Right.
But
okay.
Yeah, exactly.
So to Donnie's question, I keep doing the thing where I'm pointing the wrong way because of the so to Donnie's question, it's opposite. my room versus the screen, is the reason is I think a good way to answer this is to think about the kind of weirdness with RNA viruses, right? I think you're familiar with the idea that RNA viruses, we can't resolve relationships further in the past than like 50,000 years. And the reason for that isn't because RNA viruses didn't exist longer than that in the past. It's because they have small genomes and they mutate really fast. So it doesn't take very long to bump into a saturation problem, right? Where two sites that are the same, you cannot distinguish between similarity due to common ancestry versus similarity due to convergence due to mutation, right? That's the saturation problem. With animal genomes and eukaryotic genomes generally, we have very large genomes compared to viruses and prokaryotes, and we have genomes that have low per base per replication mutation rates on average. So it would be way far in the past, so far that we don't have to worry about it before we run up against this saturation problem. And that's the reason we're able to resolve it across these large time differences, billions of years in some cases, despite the number of differences that have accumulated. And again, it's region specific. There are some regions where you do have that problem, right? You can't use the control region of the mitochondrial DNA to compare across eukaryotic kingdoms because they're just too different. But you can use that region to compare across animal species.
But I still don't understand how substitutions won't just scramble the hierarchy signature, since, correct me if I'm wrong, those fixations are going to be due to random genetic drift, essentially, no?
Some of them will be, but in the highly constrained regions, they won't be, right? In the highly constrained regions that have...
But we're talking about the unconstrained regions and why they...
Okay, yeah. In the unconstrained regions, it's still, most of what we're talking about is going to be in the nuclear genome. So you experience a relatively low rate of per base, per replication mutations, and we have effective error checking, and you still have to contend with genetic drift, and you have to contend with the loss of diversity due to selection on linked genotypes. So you still have a bunch of things that are weeding out those mutations. They're going to accumulate faster than in the highly constrained regions, but we still don't expect them to accumulate at the per base mutation rate generation after generation, as we would expect if it was operating purely under drift because of linkage and other factors.
See, this doesn't seem consistent with your worldview. Because if you're talking about
here's the thing, it's complicated, right? Like biological systems are complicated and there's nuance. So
even complication should be compatible with your worldview. But you're talking about these highly constrained regions, and you're saying if we change them too much, well, they won't work. You literally said that, like.
Are you saying there's now? Are you still saying there's now significant selection,
Donnie? Let me
those unconstrained regions, Dan? Well, but so that's the point: is they should be drifting fixation randomly.
I want to be clear though. You can have a slower substitution rate in a region that itself is not under purifying selection. You can still have a slower than mutation rate, substitution rate in that region due to selection operating on linked regions. Follow?
Well, I follow, but
things are a thing, right? So if you have
population genetics says that your per generation neutral mutation rate equals your long-term fixation rate.
In haploid asexuals where you assume no linkage, yes, that is the case. But if you have linkage, if you have one gene that really matters, right, and you have a bunch of unconstrained stuff that's linked to it, you have mutations in the linked unconstrained regions. A lethal mutation in that gene doesn't just wipe out the bad mutation that was lethal. It also wipes out everything with it. Linked, right? That's what I'm saying, right? And that's still drift.
Okay, so you're saying that neutral mutations accumulate. I'd say nearly neutral mutations accumulate in linkage blocks. Okay. And basically they go unchecked. Selection doesn't see them, but eventually that linkage block can be hit with a deleterious mutation that is selectable. And so as a result, that entire linkage block is removed from the equation.
So on net, you're still going to have faster substitution rates in the unconstrained regions, but it's still not going to be equivalent to the per base per replication mutation rate. It's still
Aren't you assuming that enough of those kinds of deleterious mutations in these linkage blocks that have accumulated these nearly neutral mutations have to take place over the millions of years to basically answer this question of why these unconstrained sequences are not just scrambled to nothingness?
And this is
No,
not
I mean,
consistent with his worldview.
Wait,
He's
I mean,
saying,
so
he's
I
saying
want to be
these-
clear. Sorry, can I?
We'll let Dan go, and then you go next, Bubblegum.
So we can. These are totally good and legitimate questions. It's just that like we can measure the rate and we can do the math and see like if it was accumulating at this rate, here's the degree of divergence we should see. And then we could also account for things like linkage and selection on linked genotypes. Or like we can. It's complicated, but there is math we can do to do this. And when we do that, it basically works the way we expect. Like, I mean, I can get out a whiteboard and we can like do math, but nobody wants to do that.
We'll save the math open mic for next week. Okay, I have a couple thoughts, but to be fair, Bubblegum, you go ahead, and we'll just kind of run with it at this point since we're at 3.5 hours.
well, see, that's highly inconsistent with his worldview. Earlier, he said these highly constrained areas cannot be mutated too much. But that's what evolution requires in the first place. He's not going to say that these highly constrained areas were the same as they were in their first, I don't know, the first cell. So that would be a requirement. And the fact that we have error correction for mutations, the very thing that's supposed to be driving evolution, it's a contradiction. Why would life have error corrections when it is the driving force behind its survival? You can answer, Dan.
I was going to say, I mean, I was going to say I have an answer. The answer is that mutation rate is a phenotype, and there's an optimal range for it that's context specific. Sometimes you want a higher mutation rate, sometimes you want a lower mutation rate. Like, that's what it is. It's a phenotype that's context specific. You can demonstrate this in lots of different things.
Who decides that?
The environment, natural selection. You have a curve of phenotypes for that trait. Well, don't interrupt me. You ask a question, then let me answer it. If within a population, you're going to have a curve of mutation rates, and based on that level of mutation rates, some individuals are going to be more likely to survive and reproduce than others. And those individuals, if mutation rate is the salient trait in that context, then you're going to have that population shift based on selection towards the optimal mutation rate, whether it be higher or lower than the average at any given time.
Well, you're just presupposing these mutation rates were different in the past.
No. What I'm saying, like, that's actually directly observable. I've actually done that myself, where there are viruses that actually artificially elevate their mutation rate, and if you chemically mutagenize them, the mutations that they select for then bring their mutation rate back down into the range you would expect. So no, I'm not. I've directly observed the thing I just described. Sorry.
But here's the trouble. Why do we have these error correction? How do you reconcile error correction with mutations?
I just answered that.
No, you didn't. You just told me. You just like, well, I presup these mutations happen. Okay, sure, I grant you that.
All right, we do it again. Mutation rate is a phenotype, and in any given ecological context, there's going to be an optimal mutation rate. So if a higher or lower mutation rate than the current average is a salient trait for fitness in a given population, then you're going to see selection for either more strict or less strict error correction until that population gets to the optimal average mutation rate.
Sure.
And again, I have directly I've done this in the lab.
I agree with you. It'll probably, you can have mutations increase the fitness, but it will not increase its survival. So the problem are the mutations in and of themselves. Why does life have error correction? It shouldn't have error correction if your mutations are required.
Bubblegum, why are you assuming that it wouldn't? If you're saying that it would benefit their fitness but not their survival, why are you assuming that?
That's why I'm asking you. Why are you assuming that?
It doesn't track.
So, that doesn't logically follow. Why would it not be good for their survival to increase their fitness?
Just because something could be increase their fitness does not mean it increases their survival.
Yeah, explain that. Why not?
For example, I can give you an example. Let's say you're a person with AIDS, and you can attract a person who is a bug catcher. Sure, that'll increase your fitness, but that is not the survival of that population.
What? I don't even know what you're talking about.
I'm talking about fitness versus survival.
Yeah, I don't understand.
So
what you said.
when I'm talking about survival, I'm talking in the terms of population.
Why are you talking in terms of population instead of talking
Because
about
of,
in terms
because
of
of
the
because
fitness? You're saying that
I talk in terms of
fitness-
population because evolution happens in terms of population.
Yeah, so you're saying that what can increase the fitness of a population isn't good for the survival of the population?
I'm saying what can increase the fitness does not necessarily mean it'll increase the survival.
So yeah, provide an example for that, but don't use confusing terminology about bucks or something. I didn't understand what that meant.
For example, you can have let's say you have a little tribe of bug catchers. You know what a bug catcher is?
Like bug?
A bug catcher.
No, I don't know what you're talking about. Is that
It's
just
somebody
that catches
no,
insects?
no. It's a sexual term for people who are attracted to people with STDs.
Oh, okay.
So that
I
can
have
be a
no
benefit.
idea what you're talking about, man.
Donnie, can we seriously? This is
Well,
pointless.
I'm talking about what is fitness.
Can you
versus
pick a
survival.
less? Can you pick a less weird example, please?
You are talking fitness in your definition.
I have
is not
never
what
heard
you,
this term in my life.
Yeah,
We
fitness
don't need to do this.
Just
Well, are you
if what you're saying is true, then just come up with a different example of it, please.
Guys, I want to get back to the topic with Bubbles. I appreciate gave you a chance to respond.
I am on topic. I mean, they're just denying fitness. Fitness just means the ability to reproduce.
Right? No, I'm not saying you're completely off topic, but in terms of the unconstrained regions and basically the question,
I'm asking. They can't say that these constrained regions cannot be mutated past a certain level because that's contradictory to their whole worldview.
No, there are constrained sequences and there are unconstrained sequences. Nothing about that is contradictory.
You're going to have to say these constrained sequences didn't exist.
Well, I'm just curious because Dan. So, are you saying that when it comes to basically your per generation neutral mutation rate equaling a long-term substitution or fixation rate, you were saying that doesn't apply to diploid organisms?
You have to control for a bunch of other factors, is the way I would say it. So you can model it very readily in haploid asexual populations. So like this is why Jensen, for example, loves to do this for the Y chromosome and the mitochondrial DNA, because you can approximate haploid asexual populations for those two parts of the genome because they are largely but not entirely non-recombining, right? Once you put diploidy recombination, it gets more complicated.
Well, I appreciate that, but I guess my question is, here's the article that Chris Roop and I wrote, and we have this quote from evolutionary biologist Douglas Futuyma, however you say that. Futuyma.
Don't make the Jensen error. Know how to pronounce his name.
Futuyma. Say it. Okay, I'll never mess it up again. So, yeah. So he says, I guess if you can speak to this a little bit, is he agreeing with you? I mean, he's saying it would take 4 NE generations for such mutations to reach fixation. About the same number of neutral mutations should be fixed every generation. Mm-hmm. The rate of fixation mutations is theoretically constant and equals the neutral mutation rate. So the way I interpret that is your neutral mutation rate today, what we observe, will equal over time the fixation rate. Can you speak to that? I want to be
on this. This is this is the from the introductory level evolutionary textbook on this topic. When you do it for real, the math is more complicated, and that last sentence is the key there. This is the theoretical basis of the molecular clock. That is true. That is this is like the Hardy-Weinberg version of a molecular clock, right? If you know what that means, right? It's the idealized case that you don't actually find in nature. When you do this for real, it gets more complicated because there are confounding factors at play.
Okay, so you're saying this is the theoretical basis of the molecular clock. So in theory, your neutral mutation rate will equal the long-term substitution or fixation rate.
If you could isolate a sequence from all other sequences and that sequence strictly operates under genetic drift and there's no recombination, there's no inbreeding or whatever, right? It operates as a haploid. If you could You know, the if you're familiar with the phrase "a spherical chicken in a vacuum," right? That's what we're talking about here.
So so you're saying the math is complicated, the math contradicts what the theoretical basis of the
Not
molecular
contradicts,
clock.
it's just more complicated.
It's more
The
complicated.
theoretical
Okay.
model approximate it,
It's
but
multi-dimensional. So have you done the math? You said that you'd pull out your whiteboard, but you know, maybe that was tongue in cheek, but like, have you done the math to see if it's complicated enough to be different to what he's saying?
in what organism? In what organism do you want to talk about? Because for some subset of organisms, the answer is yes, I have done the math.
Well, if we're talking about human beings,
then no, I haven't done the math specifically for humans.
Well, and that's the problem I have, is because we oftentimes discuss mitochondrial Eve, Y chromosome atom. We talk about genetic entropy, and usually we're discussing humans. And so if the neutral mutation rate, the per generation neutral mutation rate equals the long-term fixation rate, but you haven't done the math.
Oh, no, I haven't personally.
Humans.
Humanity has done the math.
Okay, so it has been done. You're saying?
I have not. I thought you were asking what have I personally done the math on.
Right.
And no, I've done this for like viral phylogenetics. So I have not personally done this type of thing for human time to most recent common ancestor stuff, which is a little bit to the side of the topic we were talking about with the constrained versus unconstrained sequences. But it's I
think it goes back to the challenge I posed or advanced, that your unconstrained sequences, basically these mutations should be randomly drifting to fixation. And so
approximately
we should find those unconstrained sequences mutated to the point where there is no consistent signature or hierarchy, but we do find a hierarchy. And I find that to be curious if deep time evolution is true. So maybe it's going to depend on what organisms we're looking at, but pick your non-haploid asexual organism and let's run the math, basically.
That's fine. I mean, that's fine. I just want to be clear, though. You agree with me that we do find the nested hierarchical pattern in the sequences we're talking about, things like herbs and stuff. We agree on that, right? We find that pattern.
I agree. Yes.
Okay, great. So that is an explicit prediction of evolutionary theory.
No, but I'm showing I don't think it is a prediction, because the reasons we find that. but the question, why do we find a consistent hierarchy in those unconstrained sequences?
Because
if there's no selection or there's limited selection, mutation rate is higher in unconstrained sequences. And so over millions of years, those mutations should alter those sequences to the point where we don't find a consistent hierarchy.
I mean, that's just empirically not true, though, right? We can actually do that.
Yeah, Donnie, think about the numbers here between like the size of a genome, which is like, or the size of the total unconstrained regions in the genome. Like that would be the bottom half of your fraction there. And then think about how many neutral mutations are going towards fixation per generation, times however many generations you're talking about and the length of time that you were talking about. And just what does that fraction look like? Because you're trying to say that the numerator should be much larger than the denominator. But like think about the math involved here with the actual numbers. I think the denominator is probably going to be bigger.
Well, it sounds, again, a lot of points being made that I think need to be tested. Dan, has said that the math has been done in some creatures, but, it's something that I'll reflect on, but I still don't feel like that question has been adequately answered as to why there is a consistent hierarchy in the first place if deep time evolution is true. I understand what you're saying, Grayson, there. I understand what you're saying,
so
Dan, as well, but go ahead.
I have if it's okay with you, I have a question about something else, but I just want to wrap this up. If we want to talk about something else, great.
Okay, let's wrap up this topic. You can have the last word if you want. Go ahead. You brought it up.
It took a while to get to here, right? But we kind of got to. We agree that there are nested hierarchies in unconstrained sequences. We disagree that is a prediction of universal common ancestry. I think it self-evidently is the case that is a prediction of universal common ancestry, that you'd have these nested hierarchies. And I guess the final point is just, is that a prediction of separate creation? And the answer is no. Explicitly, it's the opposite. So the key thing that I was trying to convey all those hours ago to Kent was that the pattern that we see in these sequences, the hierarchical relationships across created kinds, right? That's a direct refutation of a prediction of separate ancestry. And there's a reason I clarified before that the separate ancestry model that Brian was talking about, that I think everybody kind of buys into, is that there's no divine tinkering as it goes on, or it's a one-time deal. And if you have that one-time creation with no tinkering, then the pattern that we observe is an explicit falsification of that hypothesis. That's the key here. I don't think I'm going to convince anybody of that, but
well, that's quite a negative.
I'm happy we're able to get to that point.
Just confirm Matt is back. So Dan, to be fair, if you did have a question,
let me just finish.
Yeah, this is a little bit behind, pulling back the curtain on the nuts and bolts of all this stuff a little bit. But my question is this: we've been sitting here chatting about this stuff with constrained and unconstrained sequences, and we've had I think a really good conversation about it. We're really digging into the weeds, and it's been an excellent conversation, getting into some really technical nitty gritty here. My question is this: this type of conversation is not possible with Kent because he doesn't know anything. He doesn't understand any of what's being talked about here. Why do you still give him the time of day? Like, he doesn't know any of this stuff. Last time I was here, he said the thing about the recombination is mom's unzips and dad's unzips and they wind up together. And like, Donnie, you know that's nonsense. You know that that's not how that works, right? Like, why do you still waste the first hour on that, and then however long in the open mic with him there? It just makes it impossible to have any kind of conversation because he doesn't know anything.
Now I can answer that question for you. Same reason modern day debate invites flat earthers and Christians to make fun of them.
Well, let's be nice to people who aren't here. I think we all have our specialties. I think we all have the areas that we focus on and understand the best. Matt and I, for example, we like to study the genetics topic because, Dan, as I think you would agree, the best possible evidence for common descent is in the world of genetics. I really believe that. And so that's the topic I like to focus on the most, and so we enjoy a good debate, and Kent's specialty may not be in the world of genetics, but I think he's got his own set of specialties, and I think he's a good debater, makes for a fun debate, entertaining debate. We like to get people in the ring, so Matt, what's your answer? And then Dan, sure, you can respond.
I think Dan triggers him too, because he said he's just reading a script again,
which is true. Tell
and
me
then
I'm wrong,
he
right?
gets mad.
Tell me I'm wrong.
Well, then he's mad. So then he's not even listening to your question.
Well, Dan and Kent, they got a love-hate relationship, so they're good at triggering each other.
No, I mean that was a good example, though, right? Because I asked, the way I approach this, and Donnie and everyone here knows this. The way I approach this is I start I try to establish a common foundation of just like definitions, right? Like, do we agree that this is what this means and this thing exists, right? And I couldn't even get that without him going to his stupid script on DNA complexity, right? And it was completely irrelevant. It was just pluck out a couple buzzwords in what I said and find the part of his script that sounded like it was related to that. It's like, it's impossible to have the kind of conversation we just had when he's present in the room. And it's like, Donnie, I see what you're trying to do with these open mics, and I will tell you, I appreciate it. And I wouldn't be here if I didn't think that this kind of conversation was valuable, right? But why do we preface it with 2 hours of that, right? That is essentially wasted time where there can be no constructive, detailed conversation like the one we're having. And I get that it's a spectacle and that's fine and all good, but even tonight, when I popped in about 30 minutes into the debate part, there were only 100 people here watching. It wasn't even like it's bringing 500 or 800 or 1,000 people to watch Kent anymore. So like, what's the value in like wasting everyone's time letting Kent recite his script for the 100th time?
Well, I appreciate the feedback. I can speak for Matt and myself. I can't necessarily speak for Kent, but we like to dig deep into these topics. These are the topics we like to focus on. And so I enjoy going into the nitty gritty. And that's usually what we do at these open mics is after the first 2 hours. You know, last week we dug deep in the hominin fossil record with Gutsy Gibbon was here as an excellent time. Week before that, we got into some other heavy topics related to, you know, the age of the earth and so on. So I guess within the 5-hour open mics, we get a little mix of everything, you know, and that's why me and whoever the host is, we'll make sure we stick around for 4 to 5 hours to allow anybody who wants to join and whatever topic people want to discuss. Like in this instance, Dan, I had a really good time discussing this topic is a great topic. And so I've had a lot of fun, and I'm glad that we've had the time to discuss it.
That's fair, and I'm gonna head out because I've been taking up a lot of time here, and I appreciate all the time you've been giving me. But I just want you to think about the cost benefit here, because you know I could see the argument if you go back like 2 or 3 years when kind of the YouTube, especially like with the pandemic, people are spending a lot more time online. You know, the debate scene drew a lot of eyeballs, right? I don't know what your views were for an average Kent debate, but it was, you know, it was up there. It was drawing a crowd. And, you know, like I haven't been paying attention for the last few months, but I popped in just over the last couple weeks to see a couple of these. And like the numbers are not what they used to be anymore. So like, you know, I hear, you know, everyone has their strengths. Everyone has the thing that they focus on. I feel like Kent's strength is the spectacles. People are saying in the chat right now, it's drawing a crowd. But like it doesn't do that anymore. So if the goal is to draw a crowd, that's not doing it. If the goal is to have an in-depth conversation, his lack of understanding of this stuff, which I mean, people are going to say that's mean, but like, tell me I'm wrong, everybody. Tell me Kent does actually have the ability to have the conversation that we've just been having for the last couple of hours. He just objectively doesn't.
I mean,
he doesn't
I
know.
will say,
So that was my conversation about universal common ancestry and what I think is the best evidence for it with Kent and SFT and Rawmatt, and there were some other people in there too. Hope you all enjoyed that. Thanks for watching. Don't get fooled.